8.1 Analysis Model. Non-isolated system, energy. The outline of this video is as follows. We will discuss the distinction between non-isolated and isolated systems. We will then identify the 6 primary mechanisms for transferring energy across a system's boundary. After that, we will address a common pitfall regarding the definition of heat. We will also cover the fundamental principle of conservation of energy and introduce the expanded conservation of energy equation. Finally, we will apply this model by looking at some conceptual examples. This slide introduces the fundamental distinction between non-isolated and isolated systems, which is essential for tracking energy. A non-isolated system is one where energy can cross its boundary, meaning it interacts with its environment. In contrast, an isolated system is defined as one that does not interact or exchange energy with its environment at all. The work kinetic energy theorem, which we have already studied, is a simple example of an energy equation for a non-isolated system. For instance, when you do work on an object by pushing it, you are transferring energy into that system. So far, work is the only transfer method we have discussed, but there are several others. The main takeaway is that the key distinction is whether or not energy crosses the system's boundary. We will now begin to identify the 6 mechanisms that allow energy to cross a system's boundary, starting with the first 3. The first mechanism is work, which we define as transferring energy by applying a force to a system that causes it to move or be displaced. The second is mechanical waves. This is a means of transferring energy by allowing a disturbance to propagate through a medium. For example, sound energy leaves a radio speaker and travels through the air to your ears. The third mechanism is heat. It is important to be precise here. Heat is a process of energy transfer that is specifically driven by a temperature difference between a system and its environment. A simple case is the handle of a spoon becoming hot when placed in coffee. Energy is transferred as heat from the hot coffee to the cooler spoon. These 3 methods, work, mechanical waves, and heat, are all ways for energy to cross a boundary. Here we will cover the final 3 mechanisms of energy transfer, completing our list of 6. The 4th mechanism is matter transfer. This happens when matter physically crosses the system's boundary, carrying energy with it. A clear example is filling a car's tank with gasoline. The gasoline itself brings energy into the system. The 5th mechanism is electrical transmissions. This involves energy transfer into or out of a system by means of electric currents. This is how any electrical appliance, like a hairdryer, receives energy. The 6th and final mechanism is electromagnetic radiation. This refers to energy traveling in the form of electromagnetic waves, such as visible light, microwaves, or radio waves. A large-scale example is the energy from the sun traveling through the vacuum of space to warm the Earth. Together, these 6 mechanisms account for all the ways energy can be transferred across a system boundary. This slide presents Figure 8.1, which provides a visual summary of the 6 energy transfer mechanisms we just discussed. Each image corresponds to one of the methods. Panel A shows work, B, mechanical waves, C, heat, D, matter transfer, E, electrical transmission, and F, electromagnetic radiation. This figure helps to anchor each transfer mechanism with a concrete, everyday example. This slide addresses a very important and common point of confusion: the misuse of the word heat. In popular language, heat is often used incorrectly, but in physics, its definition is very specific. The main point is that heat is a method of transferring energy. It is not a form of energy that can be stored within a system. We should talk about a system containing internal energy, but not containing heat. Phrases such as heat content or the heat escaped are inconsistent with the physics definition. This is similar to work. You would not say an object has work content. Both heat and work are processes of transfer. The essential takeaway is to be precise. Heat is energy in transit, driven by a temperature difference, not energy stored inside an object. This slide introduces one of the most central and powerful concepts in all of physics, the principle of conservation of energy. This principle is a fundamental law stating that energy can neither be created nor destroyed. Energy is always conserved. Because of this, if the total amount of energy within a defined system changes, it can only be because energy has crossed the boundary of that system. This transfer must happen via one of the 6 mechanisms we have discussed. A useful analogy is a bank account. The balance, which is like the system's total energy, can only change if money is transferred in or out through deposits or withdrawals. Energy does not have an internal birth or death mechanism like a population does. The essential idea is that the total energy in the universe is constant. A change in one place must be balanced by a transfer from another. This slide presents the core mathematical statement for the principle of conservation of energy. The equation is written as delta E subsystem equals the sum of T. Let us break down what this means. The term on the left, delta E subsystem, represents the total change in the energy stored within the system. This stored energy includes all types, such as kinetic, potential, and internal energy. The term on the right, sigma T, represents the sum of all energy transfers, T, that cross the system's boundary. This, T, stands for any of the 6 transfer mechanisms. For example, if 10 joules of energy enter a system as work and 3 joules leave as heat, the sum of T is 7 joules. This equation tells us the TOA, delta E subsystem, must then also be 7 joules. The main takeaway is that this equation is a concise balance sheet. The change in energy stored in the system must exactly equal the net energy transferred across the boundary. This slide shows the fully expanded version of the conservation of energy equation, which serves as our primary tool for analyzing non-isolated systems. We take our simple equation, delta E subsystem equals the sum of T, and break each side into its specific components. The left side represents the change in energy stored in the system. This is expanded into delta K for changes in kinetic energy, delta U for changes in potential energy, and delta E sub int for changes in internal energy. The right side represents all the energy transferred across the boundary. This is expanded into W for work, Q for heat, T sub mw for mechanical waves, T sub mt for matter transfer, T sub et for electrical transmission, and T sub er for electromagnetic radiation. This complete equation is our master checklist for all energy accounting in classical physics. The key idea is that the change in all stored energy on the left must equal the sum of all transferred energy on the right. This slide explains the practical strategy for applying the expanded conservation of energy equation. That single, long equation is powerful because it covers all possible situations in classical physics. You do not need to memorize many different, separate energy equations. The procedure is to start with the full, expanded equation and then analyze your specific problem. You set any terms that do not apply to your situation equal to 0. This process reduces the full equation to a much simpler one that is tailored to your problem. For example, if you apply a force to an object and the only change to the system is its speed, then only the delta K term and the W term are non-zero. The equation simplifies to delta K equals W. This shows that the work-kinetic energy theorem is simply a special case of the much broader principle of conservation of energy. This slide provides a summary of the complete analysis model for a non-isolated system. The model is a procedure for tracking energy. First, you identify the system you want to analyze, and define a clear boundary around it. Inside this system, energy can be stored in three primary forms: kinetic, potential, and internal energy. The total amount of this stored energy can change only if energy crosses the system boundary. This transfer can occur through any of the 6 mechanisms we identified, such as work, heat, or mechanical waves. The mathematical foundation of this model is the conservation of energy equation. Delta E subsystem equals the sum of T. This means the total change in energy stored inside the system must exactly equal the total amount of energy that has crossed its boundary. Let us apply our analysis model to a couple of conceptual examples to see how we simplify the full energy equation. First, consider a television set as our system. This is a non-isolated system. Energy enters via electrical transmission, which is T sub ET. Energy leaves in 3 ways: as sound, which is T sub MW, as light from the screen, which is T sub ER, and as heat to the surrounding air, which is Q. The television itself also gets warmer, so its internal energy increases, which is delta E sub int. For this system, our equation becomes delta E sub int equals Q plus T sub MW plus T sub ET plus T sub ER. As a second example, let us analyze a cup of tea being warmed in a microwave. Energy enters the system via electromagnetic radiation, T sub ER. The tea's temperature increases, so its internal energy, delta E sub int, goes up. A small amount of energy might also leave as heat, Q, to the cooler air. The simplified equation here is delta E sub int equals Q plus T sub ER. Let us walk through one final conceptual example: a gasoline-powered lawnmower. We will define the system as the mower itself, and our analysis includes the process of filling the tank. This is clearly a non-isolated system. First, let us look at the changes in energy stored times inside times the system. The blade is moving, so there is a change in kinetic energy, delta K. We added fuel, which contains chemical potential energy, so there is a change in potential energy, delta U. The engine also heats up, so there is a change in internal energy, delta E sub int. Now let us look at the energy times transferred across the boundary. Energy enters the system via matter transfer, T sub MET. When we add the gasoline, energy leaves the system in 3 ways: as work, W, done on the grass, as sound, T sub MW, and as heat, Q, from the hot engine. Therefore, the reduced conservation of energy equation for the lawnmower is delta K plus delta U plus delta E sub int equals W plus Q plus T sub M, W plus T sub MT. This slide summarizes the key concepts from our discussion of the non-isolated system model. First, we defined a non-isolated system as any system that exchanges energy with its environment. Second, we identified the 6 mechanisms that allow this energy transfer to happen: work, mechanical waves, heat, matter transfer, electrical transmission, and electromagnetic radiation. Third, we centered our discussion on the fundamental principle of conservation of energy, which states that energy is never created or destroyed, only transferred from one form to another or moved from one place to another. We express this principle mathematically with the core equation: delta E subsystem equals the sum of T. This all comes together in the full, expanded equation. This equation is our complete tool, balancing the changes in stored energy, which are kinetic, potential, and internal, with all 6 methods of energy transfer. To help you check your understanding of this material, here are 2 review questions. Pause the video and think about your answers. Question 1. What is the key difference between an isolated system and a non-isolated system regarding energy? Question 2. This question asks you to apply the expanded energy equation. A block is sliding on a rough horizontal surface and eventually comes to a stop. You can ignore any sound it makes. If you define the system as only times the block, which terms in the expanded conservation of energy equation are non-zero? Think carefully about what forms of energy are stored in the block, and what energy transfers are crossing the boundary of just the block. We will discuss the answers in our problem-solving sessions.